Hi, welcome to the theory seminars. Today's speaker is Aaradhya Pandey. He's a fifth year PhD student at the Operations Research and Financial Engineering Department at Princeton University. Prior to this, he was at IISc. He was an undergrad here from 2017 to 2021 at the Math Department. He's here today to speak to us about information, computation, and quantization. So I'll leave it to Aaradhya.
Yeah. Thanks, Sadit, and thanks for letting me speak here. So I think from the CS side, my introduction to at IISc was the course on theoretical foundations on cryptography. So I guess I'm trying to develop some theory of cryptography. But for today's talk, you will see essentially some only glimpse of cryptography, but more so to speak from the information side. And this is what I'm going to focus on today. Okay. So let's say the real title talk should be infinitely divisible privacy, but okay, overarching theme is this. Okay. So so essentially, the problem where I'm coming from is this idea called this question called differential privacy, and the idea there is that you want to really preserve people's privacy. That means, let's say you have your data somewhere on cloud, and then from there they are doing some sort of data analysis, but you don't really want outside world to know that your data is part of the data set. I mean, that's really the high level idea. And then there are multiple definitions of differential privacy that has been proposed. So I'll try to focus on this talk one of those definitions. And okay. So that's the real goal. And like in precise terms, because my background is in probability, so I'll try to develop the theory, let's say, from more abstract to some sort of concrete examples, and we'll see. Okay. So these are essentially 4 or 5 questions that I have in mind that I want to really get the idea across. And the first question is what I'm going to call the notion of F differential privacy, and then a specialization of it, which is, let's say, usually is called Gaussian differential privacy. And then these the red ones, the notion of infinitely divisible privacy and the notion of Poisson differential privacy. So these notions are, let's say, on a recent preprint. And so we'll be discussing these two. And hopefully, I'll try to give you a sneak peek on what I'm trying to do for computation, which basically means information basically means I'm trying to do some sort of statistics in some way, and you will realize that some of the things are not really computable. So what happens if I restrict to the world of computable functions, or I'll try to make precise a little bit more on that direction. And quantization basically would mean you replace probabilities with their appropriate density operators. Okay. So, and we'll also see some glimpse. Okay. So this is really the high level idea, and hopefully if you are at least have these 5 questions or 4 questions cleared up towards the end, that's roughly the goal. So so the idea that I'm trying to, or let's say this is one of the notions of privacy, is the following, is that so the way I'm trying to think about is it will be some sort of restriction on an object that I guess you're all familiar with from the CS side. It's called a randomized algorithm. So it will basically be a requirement on an algorithm. And then the question is, given this requirement, can I really construct such an algorithm that really tightly satisfies this requirement? So that's roughly on a high level the idea. And so you should think of it something along the following lines, that if you have a matrix space on the left, you have a matrix space on the right. And then you're given some sort of Lifshitz constant number, 2, 3, something like that. And then the question for you is to come up with really a function whose Lifshitz constant is actually equal to 3. Roughly, that's how you should think about it. Let's say at least the way I'm trying to present it. But the thing really is to clarify what is this function going to be. And okay, so that's roughly how I'm going to present it. So okay, so this is maybe the probability hat, let's say. The key object that you're all familiar with, and I guess from the CS side, it is usually called a randomized algorithm. What it does is, so I guess I'm hoping that you can see my cursor. So the idea is you'll have 2 sets. let's say capital omega 1 and capital omega 2. And what happens here is for every little point omega 1 on the left, you actually generate a distribution on omega 2. So this is sometimes you also call randomized algorithm, sometimes you also call randomized function. So there are multiple different names for this object, but let's say there is an equivalent description. So mathematically what it does is, this is, let's say, one definition, which is for every point on the left, you, instead of generating a point on the right, you actually generate a distribution. Okay, so I'll give some examples, but that's, let's say, the definition that we're going to keep it. We're going to keep in mind. Okay, and so this same object, hello?
Just a clarification questions.
Yes.
So this Markov kernel is defined from omega 1 cross F2, like the sigma algebra on omega 2. Why is that? Like, I'm not understanding why that is the definition, domain of the M.
Yeah, so why is that the case? Because the idea is for every little omega here, you'd like to define a sigma probability measure here on this set. So for every little omega 1 here, you want a probability measure here. So this is your state space. I don't know if that is the name you like. So
right,
yeah,
yes. The input is the domain is omega 1 cross F.
Yes.
So why F2?
So F2 is so just like, the probability measure takes subsets of the big set. So this is the big set omega 2, and M subscript omega 1 will take a subset of omega 2. So that's the idea. Okay.
So how does this correspond to the randomized algorithm case?
So
omega 1 I see as an input instance.
Yes.
How should I see F2 as?
So F2, so I'll give you some examples. Maybe that will help you clarify, I guess. So the ideal thing is the following, is that, so let's say this, if you consider this example, what happens in a random walk? So I'm hoping you're familiar with the definition of a random walk. So you should think of omega 1, omega 2 as the same, and the sigma algebra is like the entire thing, because it's a discrete, so sigma algebra never appear, let's say. Okay, they should, but okay. Now, you should think of the definition of the Markov kernel on the transition matrix that you've seen in simple random walk context is basically this one. So you go to your right with probability P, you go to your left with probability 1 minus P. Okay. So this is how I'm seeing it. So basically, you start at omega 1 and you generate a probability distribution. What is the probability distribution? It is supported on 2 points, omega 1 plus 1 and omega 1 minus 1. Right? So this description is that. I mean, if you want to really write down delta as the actual delta there is, you can remove this omega 1 and the same. So this is, let's say, one instantiation. Similarly, you can also do the same. Instead of this simpler object, you can have essentially this. So this is what I mean. So you'll have a transition matrix that maybe you're more familiar with, that like omega 1, omega 2 by omega 2 matrix, and every entry positive, and then if you take the row sums, they sum up to 1, and for every subset you just add the thing. So this is the so this is basically what I'm doing. So maybe now it is roughly clear.
Yes, thank you.
Yeah, so this is the idea. Maybe a simple random walk you have all seen. So I'm just rewriting this simple random walk in the more abstract notation, and in the abstract notation is it's a collection of probability measures. And if the collection of probability measures is Dirac, like M omega 1 is Dirac at something, then that's nothing but just literally a function. I mean, the definition of function that you've all seen in let's say +2. Okay. So, okay, so this is like the official definition, a collection of probability measures, or what you call randomized algorithm. And encryption also is the same. I mean, that's also part of it. I'll explain. And sometimes in information theory, we also call it channel. Okay, now the key thing that you should keep in mind, and this is kind of, so there are some equivalent description of a Markov kernel. And the key thing is, it takes probability measures to probability measures. It takes functions to functions. Okay, so this is important. But this is maybe the detail that so you should think of like if you have a Markov chain, then if you start at your initial distribution is P1, then you run, you hit with one step of the Markov chain, then your marginal distribution at time, let's say 1 or 2, however you want to initialize it, will be this distribution M of P1. So this you have also seen the usual matrix vector product. and this is the opposite or the correct one, whichever order you define. So this is takes functions to functions. Okay. So this is how I'm seeing. So this is some discrete examples, simple random walks and transition matrix. Now, because also we have to deal with some continuous examples, because you'll see mostly continuous, let's say roughly today. So the continuous examples to keep in mind is basically earlier when you're starting at omega 1, you're generating a 2-point distribution. Now basically you are generating a distribution which looks centered at omega 1, or let's say usually sometimes also people call it the parameter set as not omega 1 but theta, capital theta. So okay. So instead of adding a 2-point noise on your right and left, you can add a continuous noise, and that's nothing but the Gaussian distribution. And in general, if you're in a group, you can also add just a thing like a vector in a group, and that will be called convolution. Okay. So these are different ways of, so this is like the literal noise addition. You start with theta, you add a noise, and this is how you implement it, let's say, if you want to do it on a computer. Okay. So this is the idea. Now, maybe this example might interest you, but I won't really talk about too much about it. This is where you should think of this omega 1 as a finite field to the t, and the omega 2 as finite field to the n, and this n is supposedly much, much larger than t. And you are in search of interesting functions, f, that really correspond to some nice enough, interesting pseudo-random objects. So these are also actually examples of Markov kernels. So roughly what I did until now is started with the definition of a Markov kernel. I gave 2-3 examples, 2 discrete like, 2 continuous like, and one example which is like this is like an example of a function. So sometimes there's this confusion that what is the difference between a function and a randomized function. So this is like the literal function. What I mean, this is like a literally function, but a function is also a randomized function in this fashion. Okay. So so the overarching class is the randomized function, or let's say for us Markov kernels or transition kernels. Okay. So so this is like let's say one object and multiple examples, but sometimes you might have more than one object. And when you have more than one object, the starting thing is right for you to do is try to do some algebra. Just like you have 2 graphs, you'll try to do multiple algebraic operations like union of graphs, disjoint unions, Cartesian products, all possible type of products that appear when you have 2 graphs. So similarly, here is also something similar we're trying to do. And the natural things that try out is the following: that if you have more than one Markov kernels, then you can take convex combination, and that basically means you have multiple randomized algorithms to choose. With probability lambda 1, you pick M1; with probability lambda 2, you pick M2, and so on. So that's the convex combination, and the composition basically is about like you have one step of the random walk, you do second step, and you know this it becomes mu0 times p square, and so on. So this operation is basically that composition, okay? Multi-step. And in statistics also, I guess you've seen the definition that I have a statistical model p theta, and then I'm taking n samples, and somehow the distribution is p theta to the n, tensor to the n, or what appropriate notation. So this is basically that operation. So we have 2 Markov kernels. Usually in the p theta to the n case, this is also M1, and this is another way of constructing newer Markov kernels. Okay. So at least you have some feeling about what are these objects, some examples, and if you have more than one, how do you construct? The talk will essentially be about the analysis of it. That means you'll have a sequence of it. I mean, you'll not really see a sequence of Markov kernels explicitly, but the phenomena will actually be about the analysis of Markov, trying to look at some notion of convergence of Markov kernels. So, okay. So this is the entire talk, let's say, I mean, on a very high level. So you have okay, but you will not see it explicitly happening, but it is happening behind. Okay, so at least the example of Markov kernels is this phenomena is clear. So now let me actually start with differential privacy. So instead of giving you lots of examples of why it's important, I mean, I guess you're all familiar with why is it important. Let me try to actually get the definition out. So we'll take a little bit more time, but the key idea is the following: that every definition that really appears in statistics or computer science is actually a requirement on this M. And that basically means you have these 5 objects, omega 1, f1, omega 2, f2, and m. And you like to put some structures on omega 1, f2, f1, omega 2, f2, and m or roughly, let's say on a high level, forget about F1, F2, omega 1, omega 2, and M. Okay, so this is, let's say, okay, so this helps me think also for my own, let's say, thinking procedure, it helps. And okay, so there's a small comment, but I'll skip it, which is you can also think of why actually the definition of a probability distribution itself is actually a requirement on okay. So the definition of a Gaussian distribution is also a requirement on M. Okay, but here is the I guess the focus of the talk, which is we are going to discuss this notion of differential privacy. That the way I'm going to present it, at least we'll see that differential privacy is a statistical requirement on a Markov kernel. And then the moment I discuss a statistical requirement on a Markov kernel, you'll see, or at least you will remember, start remembering the statistical indistinguishability versus computational indistinguishability question. And that's basically what I'm hinting at when I say information, computation, quantization. So statistics basically for me is, let's say, the same as information requirement, some sort. You will see. And okay. So this is just a comment. I don't have much more to say as of yet, but okay. Okay, so let's try to formalize the definition of privacy. So we have this three objects, omega 1, omega 2, and M. So, so there are multiple specializations, but maybe one example to keep in mind is omega 1. You should think of it as some sort of universe of all graphs. I mean, not all graphs, but some sort of sub collection of universe of all graphs. And this is like one example. Symmetric relation basically means two graphs are related if one can be gotten from the other by removing one vertex or one edge or two edge and so on. And symmetric relation means if two elements are A related to B, then B is also related to A. This is how you define, okay, the relation. So I have put a little bit of structure on omega 1 and maybe one example to really for you to visualize. Omega 1 is not a single graph. What I'm thinking about is basically a collection of graphs. Okay, that's like the one example I had in mind, let's say. And omega 2 we'll see. Omega 2 will play different roles, but okay, there's not much requirement on omega 2 as of yet. So okay. Now, so this is the what is usually called the graph differential privacy example. But let's get back to actually the basic simpler example, where what you have is you have k people or n people, and you have their features stored, and this is basically means your set, the data set that you have is basically features of k people. So omega 1 is a product set, let's say. And then the idea is this M should be Lipschitz. When you remove one of those people and replace with another person's feature. So mathematically, it will turn out that one needs to put this notion of a metric space on omega 1. And the usual notion of metric in this context is literally the Hamming distance. So how many coordinates do they differ? So you see, omega 1 had literally no structure. We put in a matrix structure right away. And also in this canonical example that is popular is a product set. Okay.
So I had a question. So by this symmetric relation, are you kind of trying to say that these two things are indistinguishable or something? Or what is the meaning of the symmetric relation, basically?
So basically the idea is, remember when you're trying to define a Lipschitz constant, the whole point is if little x and little y are close, then f of x and f of y should also be close, right? So that basically means you need to begin with some notion of closeness in omega 1, that little x and little y are close. So the minimal requirement that you need is on the left-hand side, you don't really need a metric space, but you need some sort of notion of symmetric relation. So that when you take soup over x comma y, f of x minus f of y divided by x minus y, so you need some notion of what are you taking soup over when you're trying to define the constant. Yeah. So that's the thing that I need, a symmetric relation. Yeah. Okay. And in the context of a matrix space, the symmetric relation is basically so I define 2 points are nearby if or related if their Hamming distance, or in general a distance is less than or equal to 1. But you don't need to have any notion of distance, but you can just have set and a symmetric relation. And the example to keep in mind in this context, at least it helps me think, is this set of not all graphs, but some subclass of graphs, and two graphs are connected or related if one can be found out from the other by removing whatever procedure you do, remove a triangle, remove a, like you have to define your own notion of relation or neighborliness, and that is okay. So okay, but let's get back to the canonical example. Okay, so I'll keep the canonical example throughout, but you realize that really you can really generalize to the omega-1 and the symmetric relation case. I mean, just the definition makes sense more generally. Okay, so what is the requirement? So the requirement is the following, that if you have two data sets, omega and little omega prime, let's say, or in this context, this S and S prime, if they are really very close, then actually you want the randomized algorithm output to be close to. But remember, these are distributions, so the notion of closeness is actually through statistics. So okay, so these are distributions, so we want some notion of statistical indistinguishability. So this is how you start to see the notion of statistical indistinguishability. And I guess in cryptography, this is kind of popular, that there will also be hidden around somewhere a parameter n. And then you'll have these two distributions are statistically indistinguishable if their total variation distance is less than or equal to 1 over n to the c, or 1 over poly, 1 over poly for all poly appropriate notions of smallness. And then you also have, the moment you have this thing, then you say, wait a second, I cannot take, if in the case of total variation, I cannot take sup over all functions because that's not something I can compute. So I'll take sup over some subclass. So we'll try to do actually something very similar here, and we'll see. Okay. Okay. So yeah. So now the real departure actually technicality wise is from this line. So this line is okay. So we'll try to explain this with something called Blackwell ordering. And if people have seen, so if this might look a little bit unclear, where is this coming from? But if people have seen something called majorization, like for finite dimensional vector spaces, that means not like even for the probability simplex, if you have two probability measures with mass functions P1 through Pn, Q1 through Qn. So P's are like positive numbers between 0 through 1, and they sum up to 1. Then there is this notion of something called majorization, which is P is greater than or equal to Q if P1 is greater than or equal to Q1, P1 plus P2 is greater than or equal to Q1 plus Q2, and so on. And then the summation of Pi is equal to summation of Qi. In the case of probability, both are equal to 1. So actually that notion of ordering, the majorization, will be the finite dimensional analog of Blackwell order. Okay, so if this confuses you, keep that in mind. And I'll try to clarify if really you want to know how these two are connected. Okay, so here is where really this is how it's going to play out through this notion called Blackwell ordering. And what now I'm trying to do is abstract this out. So remember, m was supposedly a function from omega-1 to omega-2. So it was a function from omega-1 to omega-2, and for every little omega-1, it is supposed to output a distribution on omega-2. So this is the distribution on omega-2. This is another distribution on omega-2, and I want these two distributions to be nearby. So let's call this distribution P, let's call this distribution Q, abstractly on omega-2. Okay, so this is the abstraction that we have two distributions, P, Q on omega-2, and I want to really come up with a notion of that these two distributions are nearby. So here is the departure. We'll not really compute a real number. That means we are not going to compute KL divergence between P and Q. We are not going to compute total variation between P and Q, neither any generic F divergence. We are going to actually look at a curve. Okay, so this is important. We're going to look at an entire function, not like complex analysis sense, but an entire function. Okay, so the idea is, what are we going to do? So this is usually also called hypothesis testing, but also in economics, there is something called Lorentz ordering or Lorentz curve. This is also the same, some plus minus version. Okay, so what is it that I'm going to do? So here is the hypothesis testing problem, let's say, in that language, that you are given a sample. The question is, you are given a sample. You do not know where it came from, P or from Q. So the real question there is, okay, I have a sample and I don't know where it came from. So I'm supposed to devise a procedure. Okay? And a statistical procedure basically means either I should output 0 or output 1. But okay, I don't really want to do that in the sense that at least mathematically, this is not really. So you have to convexify, and then the real thing is you should output something between 0 to 1, the closed interval, not just the endpoints. Ideally, that's the target, endpoints 0 or 1. Let's say 0 corresponds to P or 1 corresponds to Q. Like, okay, in your mind. Okay, so what am I supposed to do? I'm supposed to construct a test. Okay. And test for me will be just measurable functions. Okay, you have two things, just like, you know, you have two topological spaces, you can define a notion of continuous functions. So the same thing is happening here. And the whole point is you'll make two kinds of errors. So reality is P, you're outputting Q. Reality is Q, you're outputting P. Okay, so you're going to make two kinds of errors. So, okay, so if you have two kinds of errors, there are multiple ways of minimizing. You can like take maxima, then minimize, take average, half, and then minimize over all functions phi. Here, what I'm going to do is I'm going to fix one of these errors. So there is some name that is given, but you don't have to worry. Basically, remember two errors, fix one of them and minimize the other. So I'm fixing this, what is called the type 1 error, let's say. There are multiple other names too, but okay. I'm minimizing over the other error. Now, what I'm doing is, and this is what I mean by a curve, that I'm going to vary this alpha, the level. And I'm going to vary this alpha between 0 and 1. Okay.
Hey, is this some kind of alternating minimization scheme, or are you always keeping one fixed?
Yeah.
So is there like a alternation happening?
No. There is no alternate. Yeah. So maybe let me show you a picture. So this is how it will look like. So you fix an alpha type 1 error, and then you minimize the type 2 error, and you get a alpha f of alpha, alpha 1 f of alpha 1, alpha 2 f of alpha 2. I guess you got the rough idea. Like different alphas, you will get different f's. Yeah.
Okay. Oh, I actually remember this from the last time. So yes, you can keep going.
Yeah. So this is the mathematical object remains the same. Yes. Okay.
Yes. Okay.
Yeah. Okay. Okay. So there are So this is like the information theoretic part, and we'll develop actually everything around this object. Okay. How is this information theoretic? So okay, I have a minimization problem. So obviously, by definition, I have to minimize over some set. The question is, what am I minimizing over? So here, actually, it turns out I'm minimizing over all measurable functions. And this is precisely what I mean by, okay, I missed the sigma algebra on the right, but you know what I mean. Okay, so all measurable functions. Okay, now you might say, wait a second, I don't know how to compute. So I cannot really generate a test phi. So these are also called test. Let's say if you're a computable person, you'll say, wait a second, I don't know how to generate all possible phis. So what if I minimize over a subclass of phis? What happens? So that is really the computation part. I'll have a little bit to say, but really not a fully developed theory. So this is like the same thing you do, like soup over all functions in the TV case, and then you weaken it. So, okay, so this is the computation part. And where is the quantization part? So the quantization part is the following, and this is also will come soon, let's say. Basically, P, you can replace it by rho, and Q, you replace it with by rho prime, the density operators, and tests become what is usually called POVMs. Okay, so ideally you want phi to be just like, phi to be you want it to be binary, 0 or 1. So binary things basically corresponds to indicators, and indicators become projections in whatever quantum notion. And projections are not really complete in appropriate sense, so you've got to take convex combination of projections, and the entire object becomes POVM. So you have to minimize over all POVMs. Okay, so this is how like one object but three incarnations appear. Okay, you just play a little bit, you see.
So your stochastic, so your Markov kernel now becomes a CPTP map, is it?
Yeah. So that's also natural. Yes.
Yeah. Yes. Okay. We can talk about that later.
Yeah. But so this is today's talk is about information. But I guess this object should clarify how computation and quantization really is at here. Okay. Okay. So now the official definition. Okay. So I guess if you have seen differential privacy, some version of it, you must have seen the epsilon delta. So I should start with that maybe. Okay. So basically, I will not really explain what it is, but if you have seen, it is whatever notion it appears. It is a sub, so to speak. It can be engulfed, let's say, in this bigger definition or a relaxed definition, weaker definition, whatever notion you want to call it. So in this definition. Okay. So what is this definition? Okay. So the idea is we are always going to restrict ourselves to one mathematical object. If you're really worried about there's too many introduction of notations, keep this TPQ in mind. This example is good enough mathematically. This is the cleanest object, and everything starts from here, and you can like tweak, and you get different theories. Okay. But the bigger picture again remains omega 1, omega 2. Omega 1 has a symmetric relation, and you want capital M of little omega and capital M of little omega prime to be close if omega and omega prime are close. And closeness basically in general means symmetric relation, but okay, you can talk this Hamming distance notion too. Okay. So the idea is, so this is kind of information theoretic in another sense, but so there is also a notion of informativeness as well, but I'll skip that. But the result is kind of interesting. So this is this two paper is some previous paper. It's called Gaussian Differential Privacy, and yeah, you should really try to take a look at this. It's very nice. Okay, so what it is doing, it says the following. So basically, you have this one and only one object TPQ. So you vary this P and vary this Q, and you ask what are all TPQs that you get, and why are you doing that? We'll see in a minute. The idea is we are trying to characterize what are all such functions that look like TPQ. An interesting fact that these class of functions TPQ are nothing but, so this is an if and only statement, and that's kind of powerful. Now you can start to see that interesting questions emerge. If you really switch TPQ with the computational versions and TPQ with the quantization versions. So those are actually, to my current understanding, are not fully resolved. Okay. But for the information part, you see, this is if and only if these four conditions. Okay. So somebody hands you over a function f, which is of this kind, and then ask, wait a second, do you know if this is TPQ? How do you know? How do you verify? You just have to check. Okay, your given function, is it convex? You ask. Is it continuous? Is it non-increasing? Is it satisfy this condition? If it satisfies these four, then you say, yeah. Okay, it is a TPQ. And vice versa. If you start with PQ, then you draw TPQ, it will satisfy these four conditions. Okay. Why is this important? Now, the real thing is the following. So this is the official definition. Let's say, again, in this Gaussian Differential Privacy paper, what it says is the following, that if you have this omega 1 with the symmetric relation, omega 2 with this thing, then what you're going to do is you are going to have m of little omega and m of little omega prime, and you are going to plot the trade-off function. Okay. Now, the real question is, what you want is this trade-off function to be above some curve, f. And this f, you literally want it to be T of PQ kind. Okay. So you have these two distributions, the distributions that are coming from the construction of the Markov kernel or the randomized algorithm M. And either somebody will give you a PQ that you have this baseline f, TPQ, and you should consider an M that really tightly satisfies this greater than equal to condition. Tightly means it has to be equality. I mean, okay, you know what I mean by tightness, but the idea is it has to satisfy this condition. So this is the definition of privacy that I'm going to, let's just say in this talk. And the real question now is to explain why is the definition good and so on. So I'll maybe pause for this definition if people have questions. And epsilon delta is literally the definition that you've seen in terms of log likelihood ratio within epsilon with probability delta and so on, 1 minus delta or something. That is the same as you take a specific f, and this specific f looks like this. But the moment you try to do this epsilon delta dp in terms of epsilon and delta, you're in the absolute world. That means, and we'll try to explain. But basically, if you keep this f as TPQ type, the mindset is relative errors, then actually you will see we can really talk about accumulation of errors in an optimal way. But okay, so this is the definition. I hope this is clear.
So for so you're trying to essentially find something that is at least as good as some trade-off function f.
Yes, that's the. Yes.
So you choose, in your setting, do you choose f first and then try to get something, or is it the other way? You try to find the best.
So both sides of questions are actually valid. And I'll try to get really both sides. But in this talk, or whatever, the paper or the preprint actually is about given an F, construct an optimal notion of M.
Okay.
But if you do not want to fix an F, but what you want to fix in the begin with is an M. Let's say you are fixated on one M. Then the question is, actually, you also know in CS also it's important that you don't really literally have one M. You actually have a sequence of M's. And if the problem, if you have a problem, and that you have really formulated in the correct way, in the correct notation, then actually what will happen, and this is kind of the hope, is that your trade-off functions will be a sequence of trade-off functions because you have this parameter n somewhere. And as n goes to infinity, actually your trade-off functions will converge to a limiting function. And the hope is if the limiting function looks like t of p subscript infinity, q subscript infinity, then you should take your baseline f to be literally t, p, u infinity, q infinity. Okay. So that's like the mindset. If you start with a sequence of m's, you forgot about f. You don't need a baseline. You start with a sequence of m. If it turns out that you look at this trade-off curves and they converge to some trade-off curve, then you should consider your asymptotic object as your baseline for your sequence of for your problem. So that's from
so
F.
My question was more along the lines of, say, if you suppose I say I have, like you said, suppose I have constraints on M, right? Does that inform M in any F in any way?
Yeah.
So
yeah, you put it in the correct way. So there are like papers. What they have found out is the following: is that there's something called exponential mechanism, which I won't explain today. But the idea there is the following: that you fix on one procedure M. You don't really care given a F construct M. Forgot about F. Let's say you want to start with an M. And then the real question is, what is this F then appears? But F will not appear literally when you do, I mean, F will appear. There is not a problem because this will always get a curve. But basically, in that paper, they had a sequence and the trade-off curves actually converge to some limiting trade-off curve, which looks like Gaussian. So T of normal 0, 1 and normal theta 1.
Oh, thank you very much.
Yeah. Okay. So, so this is the picture. This is how it usually looks like. And an algorithm M is said to be FDP. And you can pick any F you like. But the thought process is, do not think of absolute numbers epsilon and delta. Think of relative objects, which are TPQ type. So this is the thinking change. Okay. Now, is this going to help? And we'll see how at least one way it helps. Okay. So this is usually how the curves look like. And you see, this is kind of important. And just like in majorization, you have two distributions, but not any two distributions are really on comparable, right? You have P, little p. So forget about this entire block page. But like in your back in the mind, you have a probability mass function P, P1 through Pn, Q1 through Qn. They're not always comparable, right? Like in the majorization sense, P1 is greater than equal to Q1, P1 plus P2 is greater than equal to Q1 plus Q2. So on that probability simplex, the finite dimensional probability simplex, usually called delta n or something, there is a partial ordering, and that's a majorization ordering. But majorization ordering is a partial order. Not any two elements are comparable. The same thing happens here. Okay, so this is an infinite dimensional majorization. The idea is so this F, and if you pick a G, they might look this thing that you see. One of them is above sometimes, but crosses below sometimes. So that can happen. So incompatibility is there. Okay. I have just described the trade-off function TPQ, and the fact of statistics is the following: that if you minimize over all measurable functions, do you ask the question that is there an optimizer? And the answer is yes. And it is what is called the Neumann-Pearson lemma. What basically it says that there is an optimal choice, and it usually looks like 0 or 1. Just like that linear programming have an extremal solutions. Or even the same thing happens for infinite dimensional ones. So this is not a finite, you're not minimizing over a vector like a finite dimensional thing. Most of the cases it is like that, but sometimes you also have to actually have this randomized likelihood ratio test. But most of the cases it looks like either 0 or 1. And the key object in statistics of importance is this log likelihood ratio. Okay, but this is statistics because you're doing let's say minimizing over this, minimizing. So okay, so the optimize this. But let's say you are let's say a polynomial function, a polynomial person. That means omega 2 is something like a Euclidean space, or whose variables take real values. Okay. So then you want to define a notion of a polynomial that makes sense, or polynomial threshold functions. And let's say you are only allowed to minimize over polynomial threshold functions. Then the problem is, let's say you believe polynomial threshold functions I can compute, or I don't know, threshold functions of half spaces. Then if this log likelihood ratio is not really a threshold function, that you are in trouble. I mean, if this is not a polynomial, then you are in trouble, because then this optimizer is not. So okay, so the real question is there a computational version of Neumann-Pearson lemma? And the same thing happens. You can ask the same. Okay, TPQ replace P with rho, Q with rho prime, and okay, optimal POVMs. Okay, so okay. But this is the information question. So information, there is an answer. Okay. So this is how it usually looks like. Okay. And okay, so this is how it usually looks like, the curves. Now I'm just repeating what I said earlier, and this is basically this. Okay, so this is this idea. Now, so this is the Blackwell ordering, which I said in the finite dimensional case. Actually, if you so remember, in finite dimensional case, you had two probability measures, little p and little q. Okay, little p and little q. Actually, for this this page, think of q as p as little p0, and or capital P0, and q as P1. Okay, so there was two probability measures here. In order to compare two curves, F and G, there are four probability measures. So how is measurization connected to Blackwell ordering? The idea is basically you have to fix this Q0 to be the uniform. And if everything is P0, so omega 1 is, or omega 2 is really the unit interval with the Borel sigma algebra, then Q0 you fix to be the uniform, and Q1 you fix to be the uniform, then you'll get this. Okay. And even specialization case, if omega 2 is 1 through n, then if you fix Q0 to be uniform on 1 through n, Q1 to be uniform on 1 through n, then this ordering is nothing but measurization. Okay. So that's one way to think if you have seen measurization, but if you have not, then this is, let's say, the notion of measurization, Blackwell ordering. Okay. So this is what is called Blackwell ordering. And the idea is, if you remember the definition of TPQ, so there is only one definition you need to remember, that is TPQ. You minimize, you fix one error, you minimize the other. And you see there is an ordering. And this ordering basically means one of the problems is easier to solve than the other, because by definition, okay? Because this is the definition that TPQs have within them. Okay. And then the biggest it can become is the 1 minus x thing. Okay, that basically means P1 is equal to Q1, or in this whatever, no, TPQ, P is equal to Q. Okay, so then definitely it will be equal to 1 minus alpha. Okay, I don't know. Okay, so let's see. Now the real question is the following. So I guess from the CS, it's also kind of very important to look at something called data processing. So one important object in also differential privacy is the following: that whatever procedure that you really want to come up with them, whatever notion of privacy that you really want to come up with, actually, when you post-process your differentially private output, you should still have the same amount of privacy left. And it turns out, if you want to try that out, actually there is an if and only statement. And the way it works is, if you have two privacy curves, basically this trade-off functions, f greater than equal to g, then there is a Markov kernel that takes g to f. Yeah. So if you apply a Markov kernel, actually your curves go higher. And what does it mean to say apply a Markov kernel on a curve? I don't really mean on a curve, but basically what I mean is apply this on here. Okay. And this application of a Markov kernel goes back to the first slide, which is you should think of it as one step of the Markov chain. Okay. And the remarkable fact about Blackwell, and this is why it is called Blackwell ordering, if these two are equal, these two are equivalent. Yeah. And this also you've seen in finite dimension, that you know that P is greater than equal to Q if and only if there is a doubly stochastic matrix that takes Q to P. And you might know that stochastic matrix is already good enough a Markov kernel, but why is this doubly stochastic? And that's what I mean by that. it's just not just the case that P1 has to be go to P0. Q1 also has to go to Q0. And remember, in the majorization example, Q1 is uniform on 1 through n, Q0 is also uniform on 1 through n. And if you take uniform to uniform, actually your column sums, which is this doubly stochastic condition, also has to appear. Okay. So you have seen the finite dimensional version, I'm hoping. And so this is the infinite dimensional version of majorization. Okay. Now, okay, that's one thing. But really, have we really computed in a TPQ for us? Actually, the answer is no as of yet, except for the level of Neumann-Pearson that is already done. So, okay. Now, so this is kind of important that if you have this a TPQ where P is Gaussian and Q is also Gaussian, then actually you'll get this curve. Okay, so this is the explicit formula. Now, the key object is that if TPQ is greater than or equal to this G theta, then the interpretation is that PQ is actually always higher than a pair of normals. I mean, it is at least as difficult to distinguish PQ than a pair of normals, shifted ones, normal 0, 1 and normal theta 1. Okay. So, okay, so this, so at least by now you have hopefully remember the definition of FDP. What it says is, given an F, we have to construct an M that satisfies this condition that you is this condition. And you can okay, so this condition I've written it for the special example, the feature of K people example, but you know how to do it for graphs with the symmetric relations. Or okay. Now, so that leads and Gaussian. So this is the second question. Gaussian differential privacy is nothing but the F when you take it to be this special example. So Gaussian second question is part of first question. Okay. In fact, the third and the fourth is also part of first question, but we'll see. But these are like specialized examples, and they are kind of they appear naturally, and we'll see how they appear naturally. That's the question. Okay. So I have repeated the definition. But basically, the real question actually in differential privacy, apart from that, the post-processing has to satisfy its own condition. And this is the part of that is equivalent to Blackwell ordering or majorization. But the thinking is important that you should not think of in absolute error terms. You should think of some sort of relative error terms. And at least how does it help, at least on a symbolic level? The way it helps is the following, that let's say you have the data set and today someone asks you release average height. Tomorrow, someone asks you release average weight, and third time they ask you something, some other statistic. So you should think of like queries are coming, you are outputting something. You have to output something, but you cannot literally output 1 over n summation xi. So you have to do 1 over n summation xi plus noise. Something along those lines is what you're trying to do. And if you keep doing that, if you keep releasing more and more statistics based on the queries that you have been given, the problem that you'll have is the following, that privacy will degrade. And the question that is, if you think of absolute terms, actually you'll see absolute numbers everywhere. But if you think of this relative majorization terms or Blackwell ordering terms, actually this kind of behaves very nicely. And this is the optimal composition theorem, or what is called the general composition theorem. What it says is the following. If M1 satisfies FDP, I've not constructed an M1 that satisfies FDP, but I'm saying if M1 satisfies FDP, M2 satisfies GDP, then what does this joint thing satisfy? And this joint is basically supposed to correspond. M1 is supposed to be the randomized output, 1 over n summation xi plus noise. And M2 is some other thing, okay? Like average height, average weight, that kind of keep examples you should keep in mind. Okay. In the graph example, maybe degree of vertex 1, this could be degree of vertex 2, or number of cycles and number of, I don't know, some other subgraph. Roughly, this is something along those lines. Okay, on the network. X is the network, okay? And X is an element in, but here it is here, but you can, again, I said omega 1 can be the universe of graphs. Not all graphs, but okay. Okay. And the real question is, when you compose more than one information, what happens to your mechanism? It turns out that this behaves very nicely, and this is the real thing. That remember, in the beginning, if you had multiple Markov kernels, we are doing algebra. Now, somehow Markov kernels are gone for now. There is this baseline F or a class of Fs, these TPQs, they have appeared. Okay. Now, so this is like the class of objects that we are looking at. And let's say if I have two curves, F and G. What are all things that we can do? What are all algebras? Maybe I can take convex combination of F and G. Yes, that is allowed. That is still, if I recall correctly, is a TPQ. Here, what I'm doing is a different operation, a tensor operation. I'm defining this operation as the following. So if I start with the TPQ1, let's say little f, which is TPQ1, a little g, which is TPQ2, then F tensor G, I define it to be this. Okay. So here, what I'm trying to do is, I started with playing with this algebra on M. How does it really reduce to algebra on these curves on the right? Okay, so if I do some algebra on M side, like the left hand side of the definition, what happens on the right hand side of the definition? What kind of algebraic objects appear? And this is the object. Okay. Okay. Okay, and this is precisely what I mean by relative thinking. So this is what is happening. So your problem was earlier this much difficult, at least this much difficult, and the second output made it this much difficult. Total output, how difficult is it? The relative comparison. Okay? So that means your baseline F will now become this in the definition when you release M1 and M2 both. Okay. Now, the real, okay, so maybe in the last 6, 7 minutes, this is, I'll start with, let's say, the motivation for my results and some of the result glimpse. So the idea is, so in their paper, the Gaussian Differential Privacy paper, what they showed is the following, is that, okay, so if you compose, your privacy will degrade, okay? And the question that is in differential privacy is that you have to compose a number of things. That means a lot of number of times. People ask you something today, they keep bothering you, like ask you more questions. So if you keep asking more questions, your privacy will degrade, but how will it do so? And it turned out, and this is precisely what I mean by this error accumulation can be captured in a very nice way. You can write down probabilistic statements. So you see, literally, this is the probabilistic statement that, so if you release infinite amount of statistics, then how will your privacy look like? And Gaussian Differential Privacy paper had the name that if you assume some 4 sufficient conditions, then actually your privacy curve will converge to a TPQ, where P is Gaussian with mean and Q is Gaussian with mean and variances. And so this was their result. But the real thing for me was a very small mathematical question, at least the motivation. And this is what you see in the very subtitle, which is S square equal to 2. What they always saw is this somehow this mean and variance are related. Okay, and they saw that in all examples in their paper, in all example of interest, we always have S square equal to 2k. Why is this happening? Usually in central limit theorems, we don't see that happening. Like mean has nothing to really do with variance. They are two separate things because we have the summation xi, expectation of summation xi divided by square root of variance of summation xi. So a priori, this square root variance has nothing to do with the expectation. So what is happening? So this was the question. And basically, this was like the motivation. And then the question is, what I asked is, I'll explain now. So yes, the answer is actually turns out that yes, it will always be S square equal to 2k. And I'll explain how. But the bigger question at stake is the following. What they showed is if you compose large number of information, your privacy will degrade, but this will always become this. But the answer is, will it always remain Gaussian differential private? That means if you release this infinite amount of statistics on the same data, how will your privacy curve look like? Will it always be Gaussian? The answer is not always. And how is it? The idea is instead of really taking a generic one that satisfies these four conditions, how about I take a special example, which is I want my trade-off curve, the baseline F to be this. I am trying to distinguish between Bernoulli lambda 1 over n and Bernoulli lambda 2 over n. So this is my baseline trade-off curve. And then actually a simple computation, which also you know, which is binomials n comma lambda over n converges to Poisson in distribution. So just that fact actually gives rise to the following, that limiting object will not always be Gaussian. Okay. Under this sufficient condition, they showed, yeah, it is Gaussian, but not always. Then the natural question was, what are all things that we can ever get? Okay. And this is really one of the results. What does it say? It says the following, that if you really compose a large number of information and assume that you converge to an object of its own kind, then what will you be? Okay. So if you start with this, and you compose, that basically means you release infinite amount of statistics. What will you end up being? Okay. And the characterization in their paper is that if you assume some sufficient condition on these objects, you know F infinity has to have Gaussian. But in general, what will it be? And the characterization theorem says if you converge to an object of its own kind, it will have to be a specific trade-off curve. Okay, and this is what I mean by infinitely divisible privacy. So not all curves appear in the limit of composition. What curves appear is basically TPQ, where P is an infinitely divisible distribution and Q is a distribution which is nothing but what you've seen in Chernow bounds, and this is the exponential tilt. Okay, a change of measure as you would call it. Now, what is an infinitely divisible distribution? Whatever it is, the idea is it is infinitely divisible if it's, there's a fact that Fourier transform determine the distribution. So infinitely divisibility is basically says that there's an explicit formula for the characteristic function, and it is nothing but as a Gaussian component and what is called the Poisson process component. So the real thing to keep in mind is this infinitely divisible distributions actually capture both the central limit theorems, this first one as well as the second one. So this really combines it. And so this is part of this thing, that it really combines this thing. But let's get back to the smaller question, which is what happens if S square equal to, is it really the case that S square equal to 2k all the time for the limiting infinite object, the limiting object? It turns out, yes. Why is that the case? Actually, the reason turns out to be very simple. Here, what I showed is if you converge, you will become infinitely divisible, and this Q is also a restricted kind. So basically, it means P has to be an infinitely divisible distribution. That's the first condition on P. And the second condition on P is exponential moment of P has to be 1. Okay, so these are the two conditions. If you converge, it has to be of this kind. Now, if you, let's say, assume that P is Gaussian, because infinitely divisible distributions have two parts, a Gaussian and a Poisson process. So forget about the Poisson process part or the Poisson part. Okay, so if you have this Gaussian case, then you know a very simple fact that exponential moment of P is nothing but e to the m plus sigma square by 2. We compute it all the time. If that has to be equal to 1, because that's a probability measure, then you know why is that the case. Okay. So this is the resolution. Okay. Now, the other thing, so I have not really constructed for you a mechanism. Okay. What does this mean by mechanism? So the idea is given an F, construct an M. Given an F, construct an M. Now, the usual Fs, and this is also the part of this Gaussian differential privacy paper, or also previous mechanisms, like this is what they would call Gaussian additive mechanism. What they do is they will have a statistic to release, something like 1 over n summation xi about the data. Okay. And what they will do is they will add a noise, just a Gaussian noise with a certain variance scale such that they would actually satisfy the definition of privacy, if you remember. So here is what you see, that if you have an F, how do you construct an M? If the F is specialized, that means F is Gaussian, that means F is normal zero, the TPQ, P is normal 0, 1, and Q is normal mu 1 or normal theta 1, whatever notion you like. Then actually there is a way to construct an M. What you do is you release your statistic at hand and then add a noise of a certain variance. Okay. So this is what is usually happens when you try to do something called differentially private SGD. You just do your gradient descent, and every time you add a Gaussian noise, and there basically you say that yes, my algorithm, whatever M is, it satisfies this. It is differentially private. Now, what I asked in my paper is the following: is that what if I'm not doing SGD, but I'm releasing graph statistic? That means I have this universe of graphs, not all graphs, but universe of graphs. Or let's say for that matter, a given graph, I want to release a degree of vertex 1. I'm not doing SGD or any such thing. Then the natural thing to consider is I don't really want to be confused by normal 0 1 and normal mu 1. I really want to be confused between Poisson lambda 1 and Poisson lambda 2. Then how can I construct an M? And it turns out on the face of it, it looks complicated, but it turns out actually this is kind of goes back to the basics, which is even how do you generate a random variable on the real line? It turns out the way to generate the random variable is you start from a uniform distribution on the 0, 1, and then you compute the capital F inverse of the whatever distribution to compute, and you do F inverse of U. So this is, let's say, I have been able to construct a mechanism. So maybe I'll stop here. I guess it's already 8:35. So this is. yeah, what I said by given an F, construct an M.
Yeah. So do you want to like go over the future slides, or because I guess that will be fast? Do you want to flash it?
Yeah. I am open to both. So the future slides basically says what I also said in the last time. This kind of the thing is that so this is not related to the, but this kind of important. Like if any of you like different F divergences or any pair of any divergence measure which takes two probability measures, outputs a real number, which takes two probability measures, outputs a real number, and every such examples come out like total variation, F divergence. So the F from F divergence has nothing to do with the F that appeared in, let's say, throughout the talk. Okay, and also ring divergence and so on. All the divergence that you've heard of, if all those that satisfy what is called data processing inequality, and in my notation, you've seen probably the mutual information version, not in my notation, but in this notation. Data processing inequality basically means this the divergence decreases if you process. So okay, so if you process, your divergence decreases. Now the real thing is the following, and this is why this curve TPQ is of utmost importance, that any divergences comes through a TPQ. And the computation part I'll skip. What I did is basically, instead of replacing this bigger sigma algebra, if I replace it with the smaller sigma algebra, what happens to the TPQ curve? And it turns out the TPQ curves look like this continuous curve, but the moment you shrink your sigma algebra, that means you are on the real line, but you are on the real line. Remember, two probability Gaussian are on the real line with Borel. But if you replace this Borel sigma algebra with what I'm calling the sigma algebra generator by integers, and this is probably the first exercise you see, generate a sigma algebra which is different from the Borel sigma algebra. If you do that, that means you are restricting your class of measurable functions. Then actually it turns out that the curves are not what it was earlier. Okay, so that's it.
Okay. Any questions for the speaker?
So maybe 3 is, let's say, this paper. So the key results are, let's say, what I've shown today is a construction of a mechanism, what you'd call Poisson differential privacy. And this abstract result, which basically says under a limit of composition, how does your F's converge? If they converge, who will they be? So it's like trying to find out all the fixed points.
Okay. If there are no questions, let's thank the speaker again. And
Thank you
so much. Okay. I guess, Nirjar, you'll stop recording.
Yeah, stop.
Okay. Yeah.